Welcome all, welcome once again. This is the lecture number 5 of the deep learning course. And in this particular session, we would continue our discussion about the overfitting and optimization process into the ML domain. So, you know that what is the machine learning? You know that into the machine learning, two things are actually required. First thing is that how you define your model. So, if you define a model, then after that you have to find out the right parameter for that. Okay. So for every model there are parameter. So as you know that linear model where you say that you have for an item, if the x1 and x2 are the two x1 and x2 are the two attributes, you say that your model is going to be for example w0 plus w1 x1 plus w2 x2 if this is greater than 0 or less than 0, and your decision are going to be based on that. So this is one model. So first thing that you have to decide is that your model is going to be linear. It actually fixes what? This kind of equation. And the second part is the discovery of these actual parameter. And that is going to be dependent upon what? It is going to be dependent upon your data. This is coming from your data. So based on your data, you find out that, for example, if let's assume that your data is this. Okay, these are the one for positive examples, and these are the negative examples. These are the positive examples. Then this particular line equation of this particular line is going to be good for you. But if the data is into this particular way, I say that the positive items are here, negative items are there, then this line would suffice. So both the lines are not same. For both the lines, what is going to be different? So you know that, however, um, however, the kind of equation is going to be the same, means the type of model is going to be the same, but parameters are going to be different. So your objective into the ML is actually to work on two fronts. First front is finding out that what is the kind of model that I'm going to use, and then finding out the parameter. Here I want to very categorically want to specify this, that this particular part, that which kind of model I'm going to use, whether it should be linear or it should be a neural network or whatever. It comes from the philosophy. There is no direct way that can tell you that what should be your your model. It comes from philosophy. You think, it comes you think from your experience that looks like that these kind of model are going to be going to work for me. However, finding out this parameter can be automatized, means there could be some automated, means there could be some ways that can automatically can guide you that if you change this parameter in such way, then you would be able to find out that. And that's why the machine learning term comes. It says that the machine is automatically going to discover the right parameter for me. So machine learning is ultimately what it is going to do. It is going to give you the right parameter. So I have brought a very small example in front of you to explain some very simple things. So let's assume, for sake of simplicity only, that the item that you have x has only one. Let's assume that only one attribute x1. So if only one attribute is there, I can roughly say that the attribute is 1. Okay, attribute is x only. So if the attribute is x, so if it is a linear model, how can I represent it? W0 plus W1x, I can write like this. Okay, if only one attribute is there, I can write like this. However, instead of linear one, you can make it more complex, more powerful model, and you say that W0 plus W1x plus W2x square. Here model is more powerful because you have introduced the to the power 2. Similarly, you can increase the power and you can say that x to the power m. Now this is even more powerful model, wm. So these many number of parameters you can say. So the first model that we are going to talk about is a linear model. This is the quadratic model, and here you can say that the power n, it is a more powerful model. So if you decide on any value of m could be what? M could be 1, m could be 2, m could be 3, even 0 also. If m is 0, then the equation becomes w0 only. It is just a single constant. It may also be possible. So this is the one thing that you are going to decide, what is the how much power I want to put into the model. So M actually tells that how much power I am going to put into the model, and then when you fix it that this is the power that my model is going to have, then your task would be to find out the right values of W that are going to uh, fit best on your data. Okay, so with this example, so let me say that I am going to define a hypothesis function in this particular way. Here, as I told you, that my assumption is this, that I have only one attribute, just for the sake of simplicity. So if model has the power of M, okay, then there would be how many parameter? M, capital M plus one number of parameters I need to find out. Let me show you the data. Let's assume the data is like this. If since only one parameter is one attribute is there, I can say that X. So I don't know that what is the relationship between X and Y. So let us say that the relationship between X and Y is this. What do I mean by this? For this value of X, the Y is this value. For this value of X, the value of Y is this. For this value of X, the value of Y is this. So this, let's assume that this is what the actual curve is. Okay, let's assume that this is the actual curve, but you know that there are some inherent issues, and because of this, let's assume that you want to find out what is the value of Y at this particular X. So you know that this is the value, but since you are going to do a observation, you would be getting this value. Okay, similarly, when the X is this is the value, but you would be getting this value. So you sample multiple points on the somewhere you can also find out on the line, but the data that actually you are going to get, they are not going to be exactly on the curve. This part is clear or not, everybody? Because I think into the second class, in the class 2, we have discussed this, that because of the observation, you cannot directly measure that what is the exact value of the Y, because of some errors and noise. Exact value of Y you would not be able to get. It would be small, there would be small variation. Whether this part is clear to know you or not, there would be small variation. So if the small variation is there, and actual function, you know that actual function is not known to you. So this is what you actually get. This is what you actually get. This is given to you for the learning. The values of X and the corresponding value of Y, this is given to you, and your machine learning task is to come up with this kind of equation. You can see that here it is not possible to come up with this direct equation, because you can see that it looks like that something is like this. It is not the same kind of equation. Okay, so let us model this particular problem where my data is of this particular kind. Let us model this using this kind of equation, where I say that W0 x1 to the W1 to the W1x plus W2x square plus Wmx to the power m. Let us model this problem using this equation. One by one, I am going to increase the power of the model. First, let's assume that m is equal to 0. First, let's assume that capital M is equal to 0. If m is equal to 0, then this equation becomes what? W0. So W0 means what? That it is a constant value for all the values of X. So it is going to be a line something like this. Okay, or a line like this, or a line like this, or a line like this. Which line you are going to select? The line which have the minimum error. Okay, so first let me define the error for with respect to the any of the any of the hypothesis. Let me say that my hypothesis is this. Let me say that my hypothesis is this. What is the error? Error is the difference between the value that I am going to tell you and the value between the difference between these two. This is what the error is. So if I draw a line, if this is the line, if I draw a line like this, then the error would be this, the summation of these quantities, So can you tell me that which line is better, whether green line is better or the blue line is better? You can see the difference between the original values or the and the predicted value is lower for the green one. So it is going to be the better one. So machine learning task would be to shift this line in such a way so that it reaches to this particular one. All right. So if you can do that, if you can do that, okay, if you can do that, you'd be actually reaching to this particular scenario where this red line is going to be is going to best fit your data. Do you agree that this red line is going to be the best fit to your data, where these are the data points, these are the data points. Let's assume that these 1 2 3 4 5 6 7 8 9 10 data points are there. And if you say that model is equal to 0, it would come like this. Any problem on that? So you know that this is not a good model. This is not a good equation. So what should I do? I should increase the power of this particular model. I can say that m is equal to 1. Let me put the m is equal to 1. If I put m is equal to 1, then my equation would be something like this: w0 plus w1 x. And you know that this is going to be the equation of the line. So multiple line equation, now they can be slanted. So multiple lines can be drawn on this particular thing. And then again the same question would come, that I would pick that particular line which actually minimizes the difference between the value that is given by my line and the actual values. So maybe you can suggest that, sir, looks like that there could be a line like this that is going to be best fit, because now the distance difference between this line and the actual values are going to be minimized. Okay, so this is the condition. When the m is equal to 1, this is the line that best fit the thing. But this green is not shown to you, as I told you that this is actual model, but it is not known to you. Only the data is known to you. So this is the best fit model for you. Is it a good model? Maybe not. Then you can say that I can further increase the power by putting the m is equal to 2. If you put the m is equal to 2, then there would be some model. And if you further increase this to make it an m is equal to 3, then the model that actually reach becomes this. So what do you think, that m is equal to 3 is a sufficiently good model or not? Looks like that it is sufficiently good model, okay, because now it is a very sufficiently it sufficiently covers all the data points, and the distances between the actual points and the predicted values are going to be very less. In the same line of thought, if you think that if you further increase the power, make is m is equal to 4 5 6 7 8. So let's observe this thing when m is equal to 9. If m is equal to 9, then the best fit curve gives you the parameter in such a way so that this kind of equation you are going to get. Now, if I want to find out that what is the difference, let's compare this m is equal to 3 and m is equal to 9. So you can see that here the distance is very less. You can see that you have to find out the distance between the green and this red, and this was the difference. But here what is the difference? Because this particular curve is passing to every red curve is passing to every data point, so the difference is very less. So here, if the error was, let's assume that error was 10, here the error is 0. So if you increase the power of your model, if you sufficiently increase the power of your model is going to reduce the error by the value 0. I mean, the error could be, you can absolutely nullify the difference between the prediction and the original database. So this is where you reach. My question is that if you are only focusing on reducing the error, then out of these choices, which one is the best choice? The best choice is m is equal to 9. The best choice is m is equal to 9. This is the best choice. However, let us try to understand something more. Let's assume that I wanted to find out that what is the prediction for this x. So here I can say that for this value, the prediction, the actual value for this value of x, 1 minute, for this value of x, the actual value was this, and my model was also going to tell it this. So my error was 0. But for this point, which is very near, my model is what my model is going to give. My model is going to give this value, because you can see that this is the curve. For this particular thing, my model is going to give me this value, and actual value on the, that actual curve was this. We are thinking that actual curve should come like this. Actual value was this. You can see that for the unseen thing, this difference is going to be very large. Similarly, from here, unseen thing, if this is the value of x, we expect that if this is the value of x, we expect the value would be here, but your curve is going to give this value. Similarly here, if for this particular x, expected value is this, but your curve is going to give me this much value, you are very bad in all the cases where the data is not provided. For the point where data is provided, you are very good. But for the points where data is not provided, you are very bad. Just compare this m is equal to 3 case. Here, if I say that here, you can see that let me come here. I can say that here, if the x is this, then the difference is this. If the x is just side by some quantity, then you can see the difference is this. It is not that much difference. Okay, it's not that much different as the difference was here. So what happens that if you increase the power of model, your model becomes better. Okay, your model becomes better on the training data, but the things which are not shown to you, for them the system becomes very bad. And ultimately your objective is to be better on the things which are actually not shown. There is a question, sir, can we program it in a way that the model learns the optimum value of m also? Okay, so this is actually a very good question, that if we want to program, interesting question. So the question is this: can we program in such a way so that my system try to give me that which is the best value of m? Okay, so if you want to find out the optimal thing, means what? You want to minimize the error. Ultimately your objective would be to minimize the error. Yes or no? Ultimately, when your program would say that it is better, program would say the thing is better when your error is going to be very small. Yes, and you can see that out of all these cases, when the error is very small, when the m is very high. Okay, so you cannot leave this thing to the system. What is the problem? If we allow machine to choose m, it would choose the highest value of m. So it becomes a problem. If you let the machine to choose, machine would choose the highest power. Means it would choose that particular model which has the highest power, and that's why on the training data your system would be very good, but your thing are going to be bad on the places where the data is not provided actually. Make sense? Shaurya? So this is the one very important problem that I wanted to tell you, that if you increase the power, if you increase the power of your model, so your model would be very good and it would be very effectively learn your data. But only issue is that is going to happen is this, that it is not going to generalize well for unknown points. It has a very high error, and that is not acceptable. Okay, we would come back to this slide once again for more information. So next thing that I wanted to tell you, that we have earlier discussed that if a database is given to you, you generally divided this data into 3 parts. One is the training part, another is a testing part. Sometimes you also keep some part that is called a validation part. So into the training test, most of the time training is very large, 80% it is going to be 70% of your data, and validation is a 10% of the thing. And in total these two things they are used for the training, so they both are somehow used for the training. and using them you are actually using actually 80% of thing to make your model better. So 20%, most of the time 20% of the things you put into the testing. However, as we have discussed into the previous class, that nowadays we are into the deep learning arena where the availability of data is very large. So huge amount of data is actually needed. If huge amount of data is available to us, then 20% data is not needed for the testing, because even a small portion, maybe 1% of the data is sufficiently enough to test the things. There is another question, Rohit is right. Is it true that the increasing the value of m implies error tends to zero always? Definitely. You most of the time, this is if you increase the value of m, your error is going to reduce. Okay, because ultimately, what you are going to do, you are going to increase the power of the learner. If you are going to increase the power of the learner, it is going to learn better. Make sense? Here we are assuming that that my that my data is linearly separable. Okay, then it is always going to happen. So because you know that more powerful thing is this. And if I say if I want to be cautious, I would say that if it is not getting better, it is not getting worse. Okay, at least it should be, if m is equal to 10, if I increase m to the 11, so 11 would not be bad than the 10. At least this much I can always say. Okay, because sometimes it may be possible that you cannot increase. If this is the something would be the maximum that you can attain. So after that, no further improvement is possible, but you can say that you cannot be bad with that. If you increase, for example, from 11 to 12, it would be not this model would not be bad than the 11 or 10 or anything else. That much you can always say. Okay. So here we were discussing that you have divided the data into the training and testing partitions, and for the training partition you are going to use for the to train your system, and then if you want to evaluate your system, means the training and test partition, that what is the error. So since you are using the training one for the and you are showing this partition to the system, so the error on this would be how much? Let's assume that the error here is 80%. Let's assume that the error on this portion is 80%. So what do you expect? What would be the error on the testing one? However, you can say that, sir, anything is possible here. Here error may be 50% or 90%. Anything could be possible, but you can think that since these things are not shown to me, so and my system is not trained on them, therefore the probability of doing error on these things is higher. If the probability of doing error on this portion is higher, we most commonly expect that this error on this thing is going to be higher than 80, maybe 85%. So error on the testing partition is mostly going to be higher as compared to the error on the training partition. Are you agreeing with this? It is going to be higher than the thing on the training one. So if my model has, for example, let's assume that m is equal to 0. Let's assume that my m is equal to, m is equal to 0. And on this, my training error is this much. Training error is this much. Okay. Training error is this much. How much the testing error would be? Something higher than this, maybe this. Clear or not? Yes or no? Can you write yes or no? Let's assume that my model is 0. M is equal to 0. So I have defined my model using the parameter with m is equal to 0. And this is what my training error is. Then the testing error would be higher and it would be like this. We expect like this. If I increase this to 1, means I have increased the power of my system, power of my learning system. So this error would go down. Yes or no? This error would go down. And Above this, maybe training error can also be down. Yes, yes or no? Yes. If I further increase from 0, I have increased 1. Then if I further increase to 2, further increase my power of my model 2, maybe my system is not getting better. But as we have few minutes back seen, that it would not go up. It would be go like this. It is going to be like this. What is going to happen on the testing error? Again, testing error may also be the same. If I improve to 3, it may further go down. 4, 5, 6, 7, 8, it may remain the same. Generally, it is not going to happen. We are actually going to see this thing with respect to this example only. With respect to this example only, when I'm going to increase the value of m, what is going to happen? This particular curve has been plotted with respect to this particular problem only. That's why this behavior I'm going to see. Make sense? So you can see that the testing error is going to be down. When the m is equal to 9, means number of training examples and the model complexity is very near, then what happens that sometime it may be possible that all the points are actually covered and then it becomes 0. Error becomes 0. It may also be possible that the error becomes 0. Now every point is being covered. This curve is clear to everybody. On the same way, testing error is also going to show some kind of behavior. But here you can see that something very strange is happening over here. That till 8 it was like this, but when I made it to 9, the error becomes very high. Why it has become very high? It has become very high? So you can think that for 3, 4 things should be the curve becomes like this, okay? But after that the curve start becoming very shaky kind of thing. At the 9 you can also see that the curve is very shaky. So therefore the point which are not for which I don't use as a training one, for that the error is going to be very high. And that's why this kind of behavior is going to be shown to me, that after some time this is going to increase very much. Once again, when I increase the complexity of the model, complexity of model means power of the model. When I'm going to increase the power of model, my training error is going to reduce, and after some time it is going to be 0 training error. But the testing error, which is actually higher, can go down, and after some time it increases. Why it happens? Because after some time my model becomes specific to that particular example only. Everybody okay with that? Any questions on that? Any questions on that? So if this kind of behavior is there, so we should draw a line over here, and we could tell that my model should not have the power more than this. Otherwise it actually loses the capacity to get generalized. So we should not use any model that has the power more than this. So we should only use the model which has the uh, power till this particular value. Make sense? Make sense? This particular condition is called overfitting. This particular condition is called overfitting. If you increase your power of your model beyond a limit, then your model is error here actually goes down, but the error on the new untrained things are going to be high, and this particular condition is called the overfitting. You always want to uh, save overfitting condition. You don't want to enter into the overfitting arena. Okay. Uh, Overfitting is not good. And you may be thinking that, sir, we are into a very problematic condition here, because we don't know that what is the exact value of m. You can ask this question to me, sir, we don't know that what is the actual, what is the good value for m, and we actually wanted that if the possible value of m is, if I can take the value of m from 0 to 1000, so we are actually tempted to take the value 1000, highest value, most powerful system we want to deploy. But you told me that if we are going to use this most powerful or very good system, it is going to harm my capacity of being generalized. So what should we do? What is the right value of m? How can I know that what is the right value of m? Okay, do you understand that what I told you? That if you, let's assume that into some computational scenario, you can choose the value from of m from 0 to 1000. So definitely you would like to take the highest value, and you want to take the m is equal to 1000. But you cannot take this 1000 value, because if you take the 1000 value, then your maybe your uh, ability to generalize is actually hampered, and therefore it is not useful. Then which particular value of m I should use? Is it a question? Yes or no? Yes or no? Is it a question? Yes. So I'm going to tell you a very important thing here. Okay, focus on this. It has been seen that when the system is actually overfitting, the value of the parameter, what are the parameters? I told you, na, W's, W into the linear model, the value of W's, W0, W1, W2, Wm, they becomes very large. The case when you actually uh, overfit, these values become very large. So there could be one way, that since you don't know that what value you should use the value 1000, but you control the values of W in such a way so that they don't get very big. And actually the effect is going to be this, that your model, since you are not going to increase the value of you are actually limiting the values of W's, so your system is actually, you are restricting the system not to learn good. Okay, not to learn good, not to learn very good. Okay, learn good but not to learn very good, so that you overfit. So here is an example that actually try to show you that when m is equal to 0, the value of W0 was, as means W0, that was actually the best parameter, was 0.19 for this particular data only. For this particular data that we have shown, for when the value of m was 1, then we need two parameters, W0 and W1. Their value was 0.82 and minus 1.27. When the m was 3, the value was 0.31, 7.99 minus 25.43 and 17.37. This condition was good condition. We have few minutes back seen that this was a good condition. But when the value of m was 9, this is the case when all the values were actually, my system was actually able to cover all the points. At that time, the value of these W's is, can you see that these values? They are very large. For example, W6 is going to be minus 1061800.52. You can see that these values are very large. So if we somehow say that in my error function, what was the error function? For all the data points, you see that what is the value my model is telling you, what is the actual value, what is the difference between them, take the square of that quantity. Along with this, if you also add one more quantity, you say that norm of the vectors, norm of the vector, W vector, should also be small. If you add this thing inside the error, what is the effect? If you add this thing into the error, what is going to be? For this m is equal to 9, this particular portion becomes 0. But this portion becomes very large, because you can see that now these values are very large. So it would not like to be here. It would like to reduce these values. Okay, if these values are reduced, then whether the system would be like this only? Answer is no. Then the system would not be like that. Again, to better learn the system, here there is one more parameter, means how much importance you want to give to this particular W's. This particular parameter also you have to increase, adjust, and maybe with W is equal to minus infinite, W is equal to 0, sorry, lambda is equal to minus infinite, lambda is equal to 0. What are the values, what are these W's? This particular table actually try to show that those things. For lambda is equal to minus 18, these are the values of W's. Okay. When lambda is equal to minus 18, then these are the values that we get for the W's, and then we can come up with the right kind of hypothesis function. Are you able to understand what I told you? Earlier, we were using this particular formula to find out the error, where I was telling that what is the thing that my system is telling, what my model is telling, and what is the actual value, what is the difference between them. I want to minimize this. Minimizing this means what? For all the data points, I want to be very close to my data points. But here I'm telling that the lambda time W, norm of W should also be included into the error. So if this quantity becomes very large, my system would try to minimize this quantity. Minimizing this quantity means now you cannot go to this particular value. Your value would be something different. Okay. So for the different values of lambda, here one side it is log of lambda has been plotted, and this particular curve try to see that what is the training and testing error that is possible for me. So you get this kind of behavior. Okay. What is the usefulness of this thing? So when you find out, let's assume that you discovered that the lambda is minus 18 is good for me. You can see here that for this particular kind of quantity, you can see that your testing and training error are actually good for you. You can see that now looks like here the training and testing error are going to be very near. So you may stop somewhere here. So if you choose the parameter appropriately, your error could be reduced a much, and then your system would be regularized, and with the higher value of m also you can perform the same kind of operation. Why do parameters value becomes very large in case of overfitting? Okay, so the question is this, that why this is going to be very large. Okay, this is what the question is, that's why this value is very large. So actually what happens now that when the number of parameters are actually going to be increased, so for every additional point you have to adjust the summation of all these points so that so that you can make it 0. What do I want to say? That in this particular equation you see that if n points are there, if n number of points are there in this equation, if I add one more point and I want to make this complete quantity to be 0, if I give you one example, so this particular parameter should be such that so that the summation of all these values it should accommodate. So that's why when we keep increasing the number of data point, every parameter that is going to come to me, it have to maintain this particular summation of all these quantity to become 0. Okay. So that's why these values are getting larger and larger, and at the end they explode, and they becomes very near to the actual value. Sometime this is a very interesting observation. Sometime having the more data helps in regularization. What do I mean by this? I wanted to give you this particular table. Let's assume that there is one side m, means the power of model, and another side there is number of example. Okay, if I say that m is equal to 2, n is equal to 1, means number of training examples is 1, my model is very powerful. If n is equal to 2, then my model model is more powerful. M is equal to 2, it can learn two things, and I am going to give you only one example. It is very good example. If m is equal to, if two number of examples is given, then my model can fully learn, my error could be 0. If I give 3 example, then my model cannot learn. If I give 4 example, my model cannot learn completely. Okay, If m is equal to 5, my model even cannot learn. He have to do something, find out some middle way. So I can increase this to 3, I can increase it to 4, I can increase it to 5. If the mod power of m is equal to 5 and the number of example is also 5, then this becomes what? Again the error could be 0. Look, let me give you this thing. Assume this equation: x minus a, x minus b, x minus c, x minus d dot dot dot. Okay, if I put x is equal to a in this equation, let me just for sake of clarity, this equation, what is the highest degree of the x? Can you tell what is the highest degree of x? What is the highest degree of x? It is 4. Okay, so if I say that this is my model, if I say that this is my model, and I say that x is equal to, I can give you any 4 points x. I can give you x is equal to 3, 5, 9, and 8. So you can write x minus 3, x minus 5, x minus 9, and x minus 8. And this equation, whatever this equation comes, this is going to represent my data completely, because all the data points, all the x values can be incorporated into this thing. Whenever you put any of these values, the value becomes 0. So the highest power actually tells me that how many points I can directly learn. Okay, so m tells that how many points I can directly learn. If I am going to supply lesser number of points, then my system is even good, no problem with that. It can learn all these points. But if I increase the number of points for the learning, my system would not be able to learn. Then he have to find out some middle path so that it adjusts with all these data points. Okay, what I along with this, what I wanted to tell, that try to understand that getting the data and the model complexity. Compare these two things: model complexity and getting the data points. Okay, if I say that give me a model whose complexity is 10 and give me 10 data example, whether both are the same thing? Answer is no, because if I ask you that, can you give me one more data example? For example, let's assume that it is a image classification problem where you have in your database and few images of dogs and few images of cats. So if you take the image of dog or cat and put into your database, how many images you can put? You can very easily put 10 images. If I ask you give me one image, you can just go and click and give me. Now you have 11 images. If I ask you give me 10 more images, you can very easily go and click 10 more images and come back to me. If I ask you give me 1000 images, you can go and spend some time and give me and get me the 1000 images. But if I ask you give me 10 computers for the processing, can you give me? Maybe you can give me. But if I ask you give me 100 computers for the processing, can you give me? Just think the complexity, difficulty in finding out the model, this particular model that is needed to compute. Because if when your model has a more power, then more computational power is also needed to compute that. So if I ask you give me 100 computers, can you give me 100 computers? Maybe yes, but see that giving 10 examples to 100 example and giving 10 computers to 100 computers, whether they are same. Just think that I can ask give me 1000 examples. You go and click the 1000 images and give it to me. But if I ask you that give me 1000 computers for the computation, would you be able to give me? Answer is no, because most of the time the model complexity is not very easy to be controlled. You cannot supply a enormous infinite amount of complex model to the system. Your model has a finite complexity, but data could be means relatively very large. It is not infinite, but relatively very large as compared to the model complexity. Okay, so if you increase the number of number of examples. So into the previous example when I was on this particular slide, what with the m is equal to 9, with the m is equal to 9, so this was my model. You have seen that it was very shaky. It was passing like this. It was passing like this. But if I how many training examples I had? I had 10 training example. But if I change from 10 to 15, if number of examples I increase, so this now few more points would be here, and then he have to pass through them also. Then the shape would be something like this. Shape may be something like this. It would be more balanced. So if you increase the number of if you increase the number of training example, for example here number of training example is 15 with the same model where m is equal to 9. So earlier it was like this, but now you can see that now this kind of curve you are going to have. This part is clear. Most of the time your model complexity is not going to be as large as your number of training examples are. So if you increase the number of training examples, if you increase the training of example, here I have used 15 example, then instead of that shaky kind of curve, you reach to this particular curve which is more stable. And if you, for example here, if n is equal to 100, if 100 training examples you have, so here number of examples are 100. So you can see that your curve, red curve is going to be something like this, which is very near to the green one in our case. So when number of examples are very large, your system is going to regularize, and this is the region. Why you regularize? Because you cannot increase as you are going to increase the number of training example. Number of training example can be increased very easily, very effectively, but increasing the number of increasing the value of m means the power of the model is not that easy. Okay. I think it is 47. So let me try to introduce this thing into next 2-3 minutes, try to give you some more idea. This particular okay, the purpose of the machine learning is actually a kind of optimization. Okay, we on the data we actually come up with a function. For my data, my objective is to come up with a function that we actually here telling that it is going to be the hypothesis function, and hypothesis function is going to be parameterized with respect to the w's. So I want to find out that particular w which actually minimizes this particular quantity. So let me say that this function is a kind of error function. If I say that this is a error function jw, means for given the w, what is the error on the what is the minimum possible error that is there on my data. So if on this particular side I represent that what is the error with respect to a learning parameter w. Okay, so if I change the value of w, instead of using this, I use this or use this or use this, my error is going to change. And let's assume that the error goes into this particular way. Let's assume that the error goes into this particular way. So which is the point where there is a minimum error? So this is the point where there is a minimum error. Let me call it w asterisk. Okay, but do you know that what is the value of w asterisk? You don't know. So you start randomly somewhere. Let's assume that I start here and I call it value as a w1. So this is the value of w1. How much error I have? How much error I have? I can go up. I can see that at this particular point, this much error I have. Okay, so if I change a bit, if I increase something into this particular w, and the value becomes w1 is equal to w1 plus delta. If I change something, I change w. So how much change? There is a change into the error. So you can again come back here and you can say that new error is this. So if this is the error, so how much change is in j is there? This much is change. How much change in delta w? This is the delta w change. So I can define what is the gradient at this particular point. What is the gradient at this particular point? Gradient is tan theta is equal to delta J upon delta W. This gradient is positive. Okay, this gradient is positive. So you can see that, am I right? This gradient is positive or negative. You can see that when I am going to increase the value of W, my J is going to reduce. So this quantity is actually negative quantity. This delta W is positive. I have increased this W. This J is negative. So this is negative. This value is negative. If by increasing the value of W, I see that my gradient, my value is decreasing, and ultimately I want to decrease the thing. So I would go into this particular direction. Okay, I would try to go into this particular direction. If my gradient is negative, if gradient is negative, I go into the direction of W. I increase the W. I increase the W. Let's assume that I'm here where I call it W2. If I increase this once again by delta quantity, my next value is going to be this, and this much increase I get into delta J. So delta J upon delta W, that is going to be gradient at this particular moment. It is going to be positive. So do you like to go into this direction? Answer is no, because when you are going to increase this W, your error is going to increase. If your error is going to increase, so it is not good. You want to decrease the error, na? You want to decrease the error. So you don't want to go into this particular direction. Instead you want to go into the reverse direction. So if this value, if gradient is if is positive, then you want to decrease this. Okay, you want to decrease what? The W. You want to decrease the value of W. So the formula is that W is equal to W at any particular moment is going to be into the negative direction of the gradient, because if with the negative you want to increase, with the positive you want to decrease, with the positive you want to decrease, means you say that minus of del upon del Wj of Jw. What is this quantity? This particular quantity is the derivative of the gradient. So you want to go into the negative direction of the gradient. Whether this part is clear? That here the same thing is written, because how much change you have done, you are changing with respect to the gradient. You find out the gradient of that particular formula and you go into the reverse direction of the gradient. So if you apply this particular formula, you would be moving into the direction where your error is going to be reduced. This particular method has a name and it is called the gradient descent. This particular method has a name called gradient descent, and actually it guides you that how can you update your weights to find out the optimal value. Okay. So once again, the same thing here also. It actually says that if you see that here if you find out the gradient is going to be positive, negative, here the gradient is negative, here the gradient is positive, and with respect to the gradient you are going to use this formula to update your things so that your error is going to be reduced. There was a very interesting paper that came in 2018, visualizing the last landscape of the neural networks. I suggest you that you see this particular paper if possible. It is a very latest paper. It actually tried to plot the loss, how the loss is actually there with respect to the neural networks. So this is what the landscape is. So what does it mean? So you can see that where is the minimum value? The minimum value is here. You can see that the minimum value is here. But initially you may be here. You don't know that what is your parameter. Your parameter, based on your parameter, you may be at this particular location. If you are at this particular location, you change the things and you can come up to this particular place. Now you cannot go anywhere because everywhere there is a height. Okay, you are into the valley. For example, if you start here, you may come to this particular place and now you are into the valley. Okay, if you start over here, you can go down, maybe you can reach here and you can go inside, maybe somewhere there would be some small dip, you find out that particular value only. That is not the global minimum. If you start here, you can go maybe reach here and you can be stuck over here. So multiple locations are there where you can be stuck. To reach to this global minimum, you may start here, then only you would be able to reach this particular place. So initialization plays a very important role, that from where you are starting and whether you would be able to reach to this particular minimum or not. So this particular diagram is very interesting diagram that tells to reach to the absolute minimum, if you are starting on this particular point only, then only you can reach. So this kind of nice diagram that I have shown you here, that if you start here, the things are like this, and then you can go here. It is called the convex plot. So these kind of convex curves would may not be there to so that you can get the right kind of things. So it becomes a challenge. Okay. So that's why it is suggested that when you train the system, you use multiple iterations. First time you start by here, maybe start by here, maybe start by here. So if 2-3 times you restart the things, then ultimately you are going to somewhere. Sometime just start from here, and then you would be able to reach this particular place. Because if you start here, you can only reach this point only. Whatever training you do, every time you may not be able to reach to the best place. So that's all for today. Thank you very much. We'll continue from here into the next class.